Thank you all for being here today and for your interest. This presentation is a portion of a presentation which I've given in a number of other venues, which is more comprehensive. It actually covers legacy superhead as well as, or if you like, conventional receivers as well as SDRs. What I've done here is I've placed the emphasis on SDR testing. Performance issues in direct sampling SDR receivers. Yes, many of the standard tests for legacy receivers are also applicable to direct sampling SDRs. Of course, there are some new concepts which need to be tested and analyzed, and I'll be covering these as well. You have the usual parameters: minimum discernible signal, phase noise, which we measure as RMDR or reciprocal mixing dynamic range, front-end IMD. This has been a very contentious parameter for which the measuring methodology used in the testing of direct sampling SDRs needs to be radically different from what we're used to from the analog of conventional receiver world. Detection filter parameters, bandwidth, shape factor, and stop band attenuation. I use the term detection filter rather than IF filter because it's really a detection channel. One exception might be the new ICOM IC7300, which is a true direct sampling SDR. However, what they've done is the FPGA upconverts the baseband to a pseudo IF at 36 kilohertz to allow repurposing of an existing DSP backend, which has doubtless saved to the manufacturer quite a lot of money. But it was a good solution, which enables the users of this new radio to operate it without a major learning curve. AGC threshold and S-meter tracking. This is tested in conventional and SDR receivers alike. Notch filter depth, noise reduction and noise blanker performance, etc. Noise reduction performance, Warren has just touched on this. I use a fairly simplistic test for noise reduction. I measure SINAD, signal to interference, noise and distortion ratio, using a SINAD measuring instrument with noise reduction off and at various settings from minimum to maximum. Sensitivity and selectivity are the core parameters of all receivers. Excessive phase noise or excessive IMD limit the usable sensitivity and the effective filter stop band attenuation on any receiver. Now, when it comes to filters, yes, everybody wants brick wall filters, but we have to strike a compromise. Processing time across the filters will increase latency, and a compromise has to be struck between filter performance and latency, as we'll see further into the presentation. With the advent of fast, cost-effective ADCs, I would say that I think it's safe to say the direct sampling SDR has eclipsed its analog QSD predecessors. But of course, with every new architecture, there are new challenges. Now, a point I want to emphasize here is that notwithstanding test reports that one sees in the published, in the ham radio press, DR3 third order dynamic range has no relevance as a performance metric when evaluating an ADC. The DR3 increases with increasing test signal power. I found that it reaches a peak at about 10 dB below clipping and then drops off rapidly. The third order intercept point, which is also quoted in the ham radio literature, is meaningless because IMD in an ADC follows a quasi first order rather than a third order law. The transfer and IMD curves diverge and never intersect, therefore there cannot be an intercept point. As regards phase noise, the ADC clock is the only significant phase noise source, apart from aperture jitter in the ADC, which is a minor contributor. If we have a very low noise crystal clock oscillator, reciprocal mixing is almost a thing of the past. Unlike a conventional LO, the ADC clock's phase noise is independent of the receive frequency. Usually RMDR is so high, it's well above 100 dB, that even the very best crystal oscillators as test signal sources can be worse than the receiver. So we have the test instrument being worse than the DUT. What I do when testing phase noise with a signal generator, I put a notch filter whose stop band is centered on the test frequency in the signal path to suppress the phase or reduce the phase noise of the test signal source. Here's a typical block diagram of an RMDR test method that I use. The frequency is arbitrary. It happened to be the frequency at which that home-built notch filter came out. And so I set the signal generator to that frequency. And F0 is the frequency of maximum attenuation. Delta F is the frequency offset for the reciprocal mixing noise measurement. The receiver is tuned to F0. The signal generator is tuned to F0 and then offset by delta F, 1, 2, 5, 10, etc. kilohertz. The input power to raise the audio output by 3 dB is noted. The notch filter suppresses the signal generator phase noise at F0, thus improving measurement accuracy. RMDR is quite simply input power minus filter passband insertion loss minus MDS. Now here we have a couple of diagrams which illustrate the IP3 problem in an ADC. In a legacy receiver, we see the intercept point quite clearly. In a direct sampling SDR, there can be no intercept point. The transfer curve flattens at the clip level, and the power output rises, and then at the clip point it drops precipitately. So there's no valid intercept point that can be quoted in a test report. I can't emphasize that strongly enough. Here's a chart which I drew up from pre-existent test results on an SDR, a direct sampling SDR. In this case I used a Perseus, and also on a legacy receiver, an IC7600. You see where the, oh, I'm sorry. You see where DR3 in the SDR rises to what I've termed a sweet spot. In this case, it's about 10 dB below clipping. And then it drops off precipitately as clipping as clipping level is approached. In the legacy receiver, third order dynamic range starts high, and as the input power is increased, it drops off rapidly. You normally quote third order dynamic range at a point where the IMD product raises the output noise level of the receiver by 3 dB. This is really not possible to do with a direct sampling SDR. The chart that we've seen shows that the DR3 of a direct sampling receiver is unusable as a predictor of dynamic performance. It rises until it reaches the sweet spot and then falls off. Several colleagues and I have proposed a new method for specifying receiver IMD. We measure the absolute power of interferers, IMD products and spurs, against two-tone input power with the ITU ITUR P372 band noise levels for typical urban and rural sites at the frequency of operation as datum lines. We term this test method Ifs S, interference-free signal strength. So if you see references to Ifs S, or in my test reports on SDRs, you'll see a reference, you'll see an Ifs S curve. That's what this is all about. The point here is that if the interfering signal, be it an IMD product or a spur, is below the band noise at the user site, it doesn't matter. The band noise will mask it and the user will not hear it, so who cares? Band noise levels are typical, of course. The P372 values are typical, they're not specific to a site. If one really wants to know the noise levels at a particular site, one has to measure them and observe them. We measure the absolute amplitude of each interferer, the IMD product or spur, and draw a chart of interferer amplitude versus per tone test signal power at a 500 Hz detection or IF bandwidth. We use the rural and urban noise levels as datum lines. I will in the future be introducing the quiet rural noise level. And if the interferer is below the band noise, we can disregard it. The IFSS method eliminates the whole discussion about the sweet spot. On our direct sampling SDR, we can read the observed IMD product and interferer levels directly off the S meter or the spectrum scope if the receiver is a direct sampling SDR with a good spectrum scope and S meter, examples being the Perseus, the Flex 6000 product line, the radios using Power SDR, Open HP SDR MRX, which has an excellent band scope and an accurate S meter. The scope and S meter level calibration should be checked in any event before taking these readings. A preamp and or an active ADC driver ahead of the ADC will degrade the IMD. Note that the Ifs S curve is quasi-first order until nonlinearity in active stages ahead of the ADC introduces third order effects. This is a typical two-tone IMD test setup. It's one that Rob Sherwood and I both use. Signal generators, Rob uses HP, I use Marconi. Each generator is followed by a 30 dB gain power amplifier with an output of plus 30 dBm. The idea of the amplifiers is to prevent transhybrid leakage from throwing the signal from one generator into the other and causing IMD in the other generator. The amplifiers are followed by low-pass filters cutting off just above the test frequency, excuse me, and a 20 dB attenuator going into the combiner. The combiner is followed by a variable attenuator, part of which is a 10 dB pad right at the receiver input to ensure that the return loss seen by the by the variable attenuator or by the combiner when there's little additional attenuation is constant. And at the output of the receiver is a true RMS reading level meter. The test signal power is adjusted for desired IMD product level as read on the scope or a 3 dB increase in audio output level. Sometimes the 3 dB method will not work. It depends on the gain distribution in the receiver under test. Amplifiers A1 and A2, as I explained, buffer the signal generators to block RF sneak paths across the combiner. These are the I2R band noise levels from the curve in the ARRL handbook. On the lower bands, the band noise is of course higher. A mistake that's frequently made by amateur operators using an SDR or any other receiver for that matter on 160, 80 or 40 meters is to use a preamp. The preamp only amplifies the noise. If anything, one can actually manipulate the receiver sensitivity by introducing attenuation such that the AGC is stimulated only by the desired signal, not by noise. You don't want band noise capturing the AGC because this will desense the receiver. This is an Ifs S curve. What's interesting about it is the curve is first order, roughly, until you start seeing nonlinear effects from the preamp ahead of the ADC, and then it goes rapidly to third order as the clip point is reached. The curve also shows dramatically the effect of dither. If the ADC has on-chip dither which can be switched in and out, as does the Perseus, you can switch in the dither or take another curve and see the effect of that curve. The dotted lines here are the noise, are the noise floor of the receiver with and without dither. Other considerations for HF SDR receiver testing. The measurement of second order IMD dynamic range, DR2, is still useful in SDR testing because second order mixes in active stages ahead of the ADC can cause HF BCI as the IMD products fall into the receiver passband. Example, if you're operating on 14 megahertz and there are two strong interferers on 6 and 8 megahertz, you'll get a product in the 20 meter band. Image rejection and IF leakage measurements are not applicable to direct sampling SDRs, but an aliasing rejection test is useful. I've recently introduced an aliasing rejection test. It's a fairly simple one. You inject a signal in Nyquist zone 2 and measure the amplitude of the product in Nyquist zone 1. So your test signal is above half the sampling rate, and you look for a product below half the sampling rate. The lower the alias product, the better the anti-aliasing filter in the receiver. In the Perseus, it's possible to use the HF span software that comes with the radio, with the receiver, to display the anti-aliasing filter curve. Another new test which I've helped pioneer, I'm not the sole pioneer of it, there are colleagues who have been working with noise power ratio as well, is a test in which a broad but band-limited band of noise with a deep notch in it is applied to the receiver. The receiver is tuned to the notch. The receiver is tuned to the center frequency of a very deep band stop filter inserted in the signal path of the noise generator. The band stop filter is typically 3 kilohertz wide at the bottom of the notch and 90 dB deep. This test method was originally used in the telecom industry to characterize multi-channel analog transmission systems. What my colleagues and I have done is we've adapted NPR testing for the stress testing of HF receivers, both conventional and SDR, in a way giving a new life to equipment which would otherwise have found its way onto the scrap heap. If a complete NPR test set, the noise generator and noise receiver are available, these can be used to test two-port networks such as wideband transformers, filters and amplifiers. This will detect passive IMD in passive components. In fact, NPR is a very powerful tool for identifying sources of passive IMD in a receiver. Here are a couple of examples. Here's an NPR test screen on the Perseus. This is the notch. The notch depth as shown on the screen here is in the order of 73 dB, which is the measured noise power ratio of the Perseus. The actual filter goes about 17 dB lower. The band limits of the band pass filter are not shown. We decided to use standard band pass filters because these are part of the original test setup. And this enables me to inform a colleague who's using the same test method as to what filters I use so that he can choose the same filters and get comparable results. The lower graph is, as I mentioned, that's the aliasing filter passband as captured on the Perseus using the HF span software. In noise power ratio testing, wideband Gaussian noise from the noise generator is applied to the receiver input. The noise loading provokes added noise in the receiver due to IMD and reciprocal mixing and passive IMD generated within the receiver's front-end circuits by the noise loading, especially in the ADC. And passive IMD can occur in the preselector. You can have passive IMD in ferrite or powdered iron inductor cores, and even in some capacitors. You can have passive IMD in PIN or PN diodes used for preselector filter selection. The added noise power is a measure of the overall receiver performance. Less added noise, in other words, a deeper notch on the previous slide, equates to a better receiver. A perfect receiver will add no noise at all, but there's no such thing as a perfect receiver. The notch filter is just wider than the receiver's detection bandwidth, and it's placed at the noise generator output. The receiver is tuned to place the detection passband in the middle of the notch. Ideally, only the added noise generated by the receiver's impairments will appear in the detection passband. The NPR equals the noise power in the channel equal in bandwidth to the detection passband, but outside the notch, divided by the noise power in the detection bandwidth itself. So going back to this slide, if you imagine a channel, if you can imagine a channel equal in width to the detection channel but placed there, that gray area is the detection bandwidth. If you imagine a channel equal in bandwidth to the detection channel but placed there, and measure the noise power in it, and compare, divided by the noise power in the detection channel, you have your noise power ratio as a number. It's a number in the range, from what I've seen with the receivers I've tested, 55 to just over 90. Some of the best conventional receivers have a number in the high 80s or low 90s. Most of the SDR, most of the direct sampling SDRs I've seen, the number is in the 72, 73 to 80 range. It's partially determined by the presence or absence of passive IMD, the bandwidth of the preselector filter ahead of the ADC will have some influence on the final reading. The poor design in the front end, or the choice of components which cause passive IMD, will cause a degradation which can be quite large. This is the noise generator which I use. The upper row of filters are the band limiting filters. The lower row are the band stop filters. The instrument has, excuse me, has a built-in ALC function which ensures that the output will be constant irrespective of the insertion loss of the filters in use. The three switches above the band pass filters are filter selectors, and above each band stop filter is a filter selector. There's also a switch for turning off the output and another switch for inserting or removing the band stop filter. Another test area which I would very much like to cover, because Warren and I have been working together on this, is latency. Latency has become a big and much talked about issue in the SDR world, where if a detection channel filter is set up with a so-called brick wall response, it can produce latency up above 100 milliseconds, which can not only degrade voice operation and make the monitor, the transmitter monitor, almost unusable, but it's of critical importance in high-speed CW operation, especially QSK, and also in the digital modes. A compromise has to be struck between filter shape factor and latency. Receiver latency is measured by applying a pulse train with fast rise time to the RF input and measuring the time interval between the applied pulse and the received pulse at the audio output with a two-channel oscilloscope. CW transmitter latency is equally simple to measure. You measure the time between the leading edge of the keying waveform and the leading edge of the RF waveform appearing at the output of the transmitter, again with the oscilloscope. For SSB, what I use is a single cycle burst from a function generator applied to the audio input of the transmitter, and I measure the time between the leading edge of that and the leading edge of the burst which appears in RF form at the transmitter output. Here is a curve which Warren and I drew up of excuse me, of latency versus versus filter shape factor, with three different types of filter. The new in the newest 337 version, or then 338 of OpenHP SDR of Power SDR OpenHP SDR MRX7, there are two optional settings for the filters: low latency and linear phase. The low latency filters really have the lowest latency. I'm almost done, thanks. The low latency filters really have the lowest latency. At the cost, now, some users say it's at the cost of a slight degradation in audio output. So what Warren and the designers have done is they've allowed for linear phase to provide an option for users who are concerned about the effect of low latency on phase noise. The third curve is a previous version of 337 which didn't have this option. So we now have some pretty powerful tools for not only measuring latency, but in the case of Power SDR, Open HPSDR 338, we can actually reduce it to the point where it's no longer a problem. I have been working very closely for quite some time and continue to enjoy working with Warren and the Open HPSDR team on testing from my lab in North Vancouver, BC. So with that, the last section of the talk is a set of links which you'll be able to see when the material is available for download. With that, I'd like to thank you all for your interest and attention.
Okay, thank you very much. Are there any questions?
My call is AB4 Delta Sierra, and I have some critical point to the noise power ratio measurements. First, I start with the back. The Wandler-Goltermann noise power measurement system was constructed for a totally different examination. Yeah, it should measure the noise floor change within a full 1,000 channel systems. And for that, it was unimportant if you skip 1 or 2 channels. So the filters are totally misconstructed for what we want to